Convex coalitions. These are the topics that we'll be looking at today: marginal contribution and a theorem on a marginal contribution, and then another theorem pertaining to the core of a convex game. But first, a little recap of what we've done earlier. So these are the definitions that we've looked at. And we looked at this example of three agents. This is the set of efficient payoffs where x1 plus x2 plus x3 add up to 10. This green triangle is the set of individual rational payoffs, that is imputations. And this red trapezoid is the core, which represents the set of imputations which are also group rational. We looked at the linear programming formulation, and if a core exists, then the solution to this LP problem would be x star such that 1 transpose x star equals the value of the coalition. Otherwise, it would, the minimum 1 transpose x star would be greater than the value of the coalition if the core does not exist. Marginal contribution. Now we have a coalition game, V, N, and the coalition need not be convex. Marginal contribution, this definition, will hold for any coalition. But let's keep in mind the definition of convexity anyway, because in this lecture we shall be dealing mostly with convex coalitions. So, given any two subcoalitions C, D of N, V C union D, the value of C union D is always greater than equal to value of C plus value of D minus value of C intersection D. Now let's come to the definition of marginal contribution of an agent I to a coalition C not containing I. That marginal contribution is delta VCI, which is equal to the value of the coalition when I joins the coalition minus the value of the coalition, C. So this is the definition of the marginal contribution of agent I to the coalition C. It's the increment in the value of the coalition when I joins the coalition. And here are so many examples. Now, let's take up this first case. We have a coalition A and A comma B and I equals C. So C is the new agent that joins the coalition. And so what's the marginal contribution of C? Before C joined, it was 2, and after C joined, the coalition would be ABC, so it became 7. So 7 minus 2 equals 5. And when C equals A, then the marginal contribution is V of AC, this minus V of A, which is there's a small typo here. This should be, let's make this a 1 instead of a 0. It should be a 1 here. So 3 minus 1 equals 2. And when C is the null coalition and I equals C, then the incremental or a marginal contribution of the agent is 1. So you can observe one thing here. As the coalition increases, the marginal contribution of the same agent C is also increasing. It's 1 when the coalition we considered was the null coalition. It's equal to 2 when C equals A, and it's 5 when C equals AB. In other words, in this case, we see that the marginal contribution of this agent C increases when it joins a bigger coalition. And that's one of the properties we shall see of a convex game. The marginal contribution will keep increasing when the coalition size increases. Theorem, marginal contribution. So here's the theorem. Vn is a convex game if and only if for all I not in C, and we have D is a subset of C. So we have a coalition C that does not include I, and we have D, which is a subset of C. Obviously, D wouldn't contain this agent I either. Then the contribution of I to C is greater than equal to the contribution of I to D, the smaller coalition D. And this is what we have to prove. So this, in fact, is an alternative definition of a convex game. So this was one definition, one condition which a convex game had to satisfy. And this is an alternate condition. If the game satisfies this condition, then it is a convex game. So let's look at the proof. First, so these are the two statements. We'll show that statement 1 and statement 2 are equivalent. So first we'll show that 1 implies 2. So part 1 of the proof, I assume that statement 1 holds. This is the original definition of a convex coalition. And then we have to show that this property holds. The marginal contribution of agent I to the larger coalition C is greater than equal to the marginal contribution to the smaller coalition D, which is a subset of C. And here I use C and E because this property holds for any pair of coalitions. So I just choose to name my coalitions C and E here. Now, suppose I have D is a subset of C, and I have an agent I which does not belong to C. So this is my C. This shaded region is C, and a subset of C is D, and this is I, an agent which does not belong to C. And I define my E as D union I. So this is my D. Excuse me, E. E is D union I. Whence I observe that C union E is the same thing as C union I. This is C and this is E, the dotted lines. C union E is the same thing as C union I. Furthermore, C intersection E equals D. This is C, and this dotted line is E, and their intersection is this smaller set D. So C intersection E equals D. Now, from my assumption, value of C union E is greater than value of C plus value of E minus value of C intersection E. From this assumption here, property 1. Whence, now I use these equalities. C union E are replaced with C union I, and here instead of E, I replace it with D union I, because E is D union I, and here C intersection E is D, so I replace it with D. Whence I get from this expression, I directly obtain value of C union I greater than equal to value of C plus value of D union I minus value of D. Or, rearranging terms, value of C union I minus value of C greater than equal to value of D union I minus value of D. Now, if you look at the left-hand side here, this is the definition of the marginal contribution of I to C. So, delta VCI is greater than, and on this side, you have the expression for the marginal contribution I to coalition D. So that's delta VDI. So whence I showed that this property holds. This property 2 holds under the assumption that 1 holds. Now I have to prove the opposite, that assuming statement 2 holds, I have to prove statement 1. That's a little more complicated. So let's go into that second part of the proof. Next, I will assume that statement 2 holds, that is the marginal contribution to coalition A will be more than the marginal contribution to coalition B if B is a subset of A. Now I have to show this statement 1, VC union D is greater than equal to VC plus VD minus VC intersection D. And this should hold for any two coalitions C and D. So let's take this as the coalition D and this as the coalition C. And everything that's in C but not in D, I will call this set S. And the agents in S will be indexed I1, I2 until IS. Next, I define the sets B and A as shown here. So B equals, first note that this is C intersection D. And so B is C intersection D union of these I1, I2 until Ik minus 1. And A is a superset of B. It's all of D plus these agents I1, I2 until Ik minus 1. And since B is a subset of A, this must hold. The marginal contribution of any agent I not in A to A should be greater than or equal to the marginal contribution of I to B. Now I write this expression VC minus VC intersection D on the left hand side, and on the right hand side what I have is all these terms, but you can see that I have negative VC intersection D here, and instead of VC I have this VC intersection D union S. But look at all the other terms. VC intersection D union I1 negative of VC intersection D union I1. So this and this cancel off. Likewise, VC intersection D union I1, I2, and again minus VC intersection D union I1, I2. So these two cancel out. And likewise, this and this cancel out, this and this cancel out, so that on the right hand side I have this V C intersection D union S minus V C intersection D. But C is equal to C intersection D union S. Hence, this is equal to V of C, whence the left hand side is equal to the right hand side. Now what I'll do is I'll look at every pair of terms on this side. This is VC intersection D union I1 minus VC intersection D. This is also, you can recognize, this is the marginal contribution of I1 to VC intersection D. These two terms I will replace with another term which is bigger than these two terms. Therefore, I will be replacing this with a less than equal to sign. And I'll do the same thing for these two terms here. I'll take these two terms here and I'll replace them with something that's more than these two terms together. And I'll keep on doing the same thing. And therefore, this less than equal to will hold everywhere. So now let's look at the first term here. This term is nothing but the marginal contribution of agent I1 to C intersection D. This here, C intersection D, the contribution of I1 to C intersection D. And this, because this property holds, these two terms together will be less than the marginal contribution of the same agent I1 to this bigger set D. So I have replaced the equal with the less than equal sign, and I have replaced those two terms with these two, which together is the marginal contribution of I1 to this larger set D here. And I will repeat the same process for every pair of terms. Now, for additional clarity, you can see what's being done here. This B is C intersection D and A is D, and then I'm invoking this property here. This is the right-hand side of this expression, which is equal to this, and this is the left-hand side of this expression, whence I get this less than equal to. Now I repeat the same thing with these two terms here. So this is the marginal contribution of agent I2 to this set here, C intersection D union I1, and I'll replace it with V of D union I1 I2 minus V D union I1, which is the marginal contribution of I2 to D union I1. And clearly this less than equal to holds. And I'll keep repeating the process. So this will be replaced with this. And in general, these two terms here will be replaced with this. And everywhere, you see, after the replacement, the right-hand side becomes larger, and so this less than equal to holds until the last one. So now I have this expression on the right-hand side, and I have this less than equal to here. Now this V of D union S, this is the set D union S, and it's the same thing as D union C. So I've replaced D union S with D union C. Whence this is what I have. And now I'll start cancelling terms. See, this is V D union I1. This is negative V D union I1. I cancel this. I cancel this and this. Both sides are plus and minus of V D union I1 I2. Likewise, I cancel everything out. And what I'm left with is this. VC minus VC intersection D is less than equal to VD union C minus VD. Whence, rearranging terms, I get this expression VC union D greater than equal to VC plus VD minus VC intersection D. And this is the statement that we wanted to prove. This is proved now. So we have proved this theorem here, and this gives us an alternative definition of a convex coalition.